Okay, conservation of mechanical energy. So the big thing here is, I mean, this is kind of review, but energy can't be created and it can't be destroyed, same as matter. All right, so we can't just magically have something have more or less energy. It can have less energy as long as we can track where it's gone. It did work on something, okay, and so it lost the energy to that something, okay, or work was done on it and it gained energy. So it's fine if the energy goes up or down as long as we can account for where it came from and it wasn't just created out of nothing. We also need to understand that energy can be converted from one form to another, specifically, as we looked at yesterday, from potential into kinetic and kinetic back into potential. Right? And then we're going to use that concept to calculate other variables like we did in the roller coaster question at the end of class yesterday. Okay? That's basically what we're progressing towards. Nothing new. We did that in science. Okay. So we know there's two kinds of energy, at least, that we're dealing with in this unit. There's obviously more than that. Okay, there's different kinds of potential energy. But we're looking at basically gravitational potential and kinetic. Okay, when you add those together, you get the total mechanical energy of an object or a system. What we've been working on up to this point is this idea. That work is the change in energy. Meaning I take the final kinetic, I add it to the final potential, and then I subtract the initial kinetic plus the initial potential. That's the stuff we've been working on. That's work energy theorem. Okay? In the real world, it's why a roller coaster can't go back up to the top of the first hill on its own. Okay? You may not have noticed this, but every classic roller coaster is towed to the top of a very high hill and then just released. And it goes through all the rest of the track. But there's never a point on the track where it's anywhere close to the top of the first hill again. Because it would never have enough energy to get back there. Okay? It loses energy to what we call non-conservative forces. That is that they make it look like energy is not conserved because the object can't get back to where it started. Okay? If a roller coaster were perfectly frictionless, it would be way faster, okay? And it would just cycle constantly. Okay? It would be like the endless ride, which for some people would be awesome, and for other people would be a puke fest, which has also happened on the trip, sometimes on others. All right, so that's what we've been looking at. That's work against non-conservative forces. If there's no work against non-conservative forces, then then EF minus EI equals 0. And if that's the case, EF and EI are the same, right? They're equal. And that's what we're dealing with in a law of conservation of mechanical energy situation. We're saying there are no non-conservative forces. The object is doing no work, no mechanical work on anything else. So its initial energy and its final energy are equal. Okay? So that means that up here at the top of the hill, there's a lot of potential because it's very high, and very little kinetic because you wouldn't be moving very fast here. When you're down here, you can't go any lower. You're at ground level. So you have your minimum amount of potential energy, 0, and your maximum amount of kinetic energy. You're going the fastest down here. Okay? And then if you go up over a bump, okay, well then your potential energy goes up and your kinetic energy goes down, because as you go up a hill, naturally you slow down. You're converting your kinetic energy back into potential. And that's all that happens on a roller coaster. If we were watching like a graph showing the amount of potential and kinetic energy on a roller coaster, it would just constantly be doing this, switching back and forth. Okay, potential energy go down, kinetic goes up. Okay, kinetic goes down, potential goes up. And then just keep switching back and forth. Okay, are you kind of all right with that idea? All right, so the final mechanical energy in a conserved situation is equal to the initial. In a non-conserved situation, the total energy is still the same, but it's not all mechanical anymore. Okay, some of it will be thermal, heat. Some of it will be sound. Okay, light even. Okay, all these other forms of energy that have to come from the initial source, which is the mechanical energy of the object. Okay, that represents work against non-conservative forces. If you've ever stood next to a roller coaster, okay, minus the sound of the screaming occupants, it's very loud. Okay? There's a lot of friction on a roller coaster because you've got metal on metal, okay, as the roller coaster goes around. That's what makes them safe, because a roller coaster typically has like a track that's made out of metal pipe, and then each car has a kind of a clamped system of wheels. So there's a wheel on the top and a wheel on the bottom that squeeze the pipe in between. Okay? If they didn't have that, then it would be possible for the carts to tip and go off the track. Or if they went over a really steep rise, they could get airborne and come off the track. Or if it went upside down, it could come off the track. So they have these wheels that squeeze the pipe, okay, so that it can't come off. Well, that creates a lot of friction, because we know the harder you squeeze two surfaces together, the more friction there is. Okay, so there's actually a lot of friction in a roller coaster. And if you look at the Mindbender as an example, or even the roller coaster at Callaway Park, you got that long part there where you get towed up to the top, okay? And then, you go down and you go up these things and you go through these loops, this loop, okay? But everything gets progressively lower until you're back where you start, but nothing's ever anywhere close to the height of the first hill, because so much energy is lost to friction along the course. Okay? Same thing like in the log ride, done the log ride? Okay? Like you get going really fast, then you hit the water, boom, and you just slow right down. All your mechanical energy gets taken away by the water, the resistance of the water. Okay? Which is why you have to get towed back up to the top of the next one that you're going to go get. All right, so principle of conservation of mechanical energy tells us kind of how the physical universe operates. It tells us kind of where does energy go, right? In any given situation, okay, what does it become? And then you see things like this where people have been really smart. I know you're probably looking at this right now and going, it's a ramp. It is a ramp. It's also brilliant, okay? Back when I used to coach track and field, we went to provincials in Edmonton, and this is at the shot put area, this little shot put return device. Okay? And while it looks like, yeah, sure, it's just a ramp, you put the shot put on the top of it and it rolls down and goes back to the throwing area. Well, it doesn't just go back to the throwing area. It goes down that track, and by the time it gets to the end of the track, it's stopped. And it stops right at the end. Somebody figured out how long and how much friction there would be along the length of that level part of track. They figured out how much energy would be lost by a shot put to friction along that track, and then built a ramp that was high enough to account for it. So that every time you put a shot put, regardless of its mass, on the top of that ramp and let it go, it would roll to the end and stop. Okay? Most people don't notice that, but I'm a physics guy, so I noticed it. And then I went and got the whole track team. And this is what I looked like when I did. Guys, you gotta come and see this! Because I was like totally excited, because like I'm a physics guy and I'm a nerd and I can totally live with that. That's what I am. And I like dragging them all over, like, look! What? So disappointing. Watch the shot put. You know, like, so? It's like downhill. It stops right at the end. It's not like the bowling alley, right? Where you can, every time you go there, some kid gets his fingers smashed between the bowling balls. Okay, it happens every single time, because they come whipping up that track, coming back from the collection area, and they hit that little thing that's supposed to slow them down a little bit, and they still smash into each other in the collection area. Well, this thing would make sure nobody's fingers ever get smashed, because the shot put just rolls to a stop. Okay? Even if there was still another shot put sitting there, the next one coming in would be going so slow that it couldn't hurt your fingers. Okay? You wouldn't get a little pinch. Okay? You certainly wouldn't like smash your fingers and hear screaming kids, okay, after that. All right, so it's those kind of applications that we can kind of use for this. All right, so real world applications, kind of tragic real world application. Back in 2010, when the Olympics were in Vancouver, one of the newer events was the skeleton, okay, which is like if the luge is not crazy enough for you, you can do the luge head first. Okay, skeleton is just luge where you go down head first instead of feet first. Okay, and so they had built this brand new track for this kind of new event, and during the training runs, Vancouver or Whistler had gotten a bunch of freezing rain. And I mean, you guys know what freezing rain does to roads and sidewalks, right? Well, imagine you've already got a track that's designed to be slippery. Then you get a nice coat of perfectly slick, near frictionless freezing rain ice deposited on it overnight. Okay? One of the people doing a practice run got in this thing and got going, and there was so little friction, so much less than they had designed the track around, that he got going so fast he flew out of the first corner and was killed. Okay, so they've got to fix this now. Like, obviously you can't let other people run down this thing, it's dangerous. But they still needed it for competition. So what do you suppose their solution was? There was, knowing that there was nothing they could do about the lack of friction. Again, there's nothing they could do about the lack of friction. You can't throw gravel on it with the little blades, right? It would actually be more dangerous if like one blade caught the gravel and one didn't. It could flip the sleds over. Okay, a braking system like in a drag race, probably that could work, but again, these are people trying to set Olympic records and win a medal. They still want to race. Okay, yes, and they did do that, but that still, people would still fly out of the corner. They just hit the barrier. Okay? How can we make sure that they're not going fast enough to get out of there? Mass won't make a difference. Remember, mass canceled yesterday when we were doing that calculation?
Airbags on the sled.
Not a safety thing. It's an energy thing. If they have so much energy when they get to that corner that they're going so fast they fly out, how can I make sure they don't have that much energy when they get there? Yeah, they couldn't really change that part of it.
Could they reduce the distance?
Yeah, start lower. If I start lower, do I have less initial potential energy? Because you can't tell people, don't run so fast. Because if you've ever watched Skeleton, they basically hold the sled. They're like a little kid, okay, at a sledding hill. They run really fast and jump onto their sled, okay, like head first. So it's kind of like that. And you're not going to tell Olympic athletes, hey, you know what, like we're all going to get a medal. They're gonna run at it. So they just put them lower. Okay? They made the start of the track lower so they wouldn't have enough energy to fly out of the track when they got to that corner. Okay? It was a simple law of conservation of mechanical energy solution. If you have too much energy when you get there, I'll make sure you don't have that much energy when you get there. And the only way to do that doesn't make the athletes have to modify what they do, is to modify where you start. Okay? Everybody all right with that idea? All right. It's kind of also like the Mega Whoosh video that we watched with the Mythbusters. Remember, they started from 3 different heights. There was the one where he barely got off the end of the track, and then there was the one a little higher where he went a little ways, and then he started at the top. Okay, moving up means that you have more energy, and thus you'll be going faster when you get shot off the end of the slot. Okay? And so it's kind of the same thing here. Right? So all we're seeing with this diagram is that the mechanical energy, that's this column here, never changes. But at the top, we've got no kinetic energy because we're not moving. All of our energy is potential. And then as we go down the track, when we get to that point there, we're moving faster, but we're lower. We've just converted the potential into kinetic. Okay, a little bit lower, more kinetic than potential because now we're more than halfway down. And then when we get to the bottom and can't go any lower, all of our mechanical energy is now kinetic. Okay, everybody okay with the idea there, the concept of it? All right, I want you guys to see if you can figure this one out. It's just like the roller coaster question we did yesterday. Okay, so we got this person who's trying to jump a canyon on a motorcycle. I'm going to show you a video of a guy jumping a canyon on a motorcycle after this. Okay, so he's going to ride off one side at 38 meters per second. The starting side is 70 meters above the bottom of the canyon. When he lands on the other side, he's only 35 meters above the bottom of the canyon. How fast is he going on the other side? Okay. Assuming there's no air resistance, this is the perfect physical world, and energy is conserved between point A and point B. Okay, give you a couple minutes on that. All right, so what we know in this question, okay, because we're kind of told that energy is conserved, right, is that we know VI, we know HI, we know HF, and we're looking for VF. Okay, so we start out as we would start out with any conservation of energy question. And we write out the law of conservation of energy. Initial equals final. Okay, it all has to be there and all has to be accounted for. Okay, what that's going to mean then is that I'm going to take EP initial, okay, plus EK initial equals EP final plus EK final. Okay, everyone all right with my expansion there? Right, and then I can expand it out even further and say, all right, M times G times H initial plus 1/2 MV initial squared equals M times G times H final plus 1/2 MV final squared. All right, they told me the mass of the motorcycle, but do I need it? I would if I was actually calculating like the final energy, because mass is part of energy. But what I'm doing here, mass has no effect on. This is just gravity, and gravity affects everything equally. Right? So I can cancel mass. Right? And I'm solving for VF. So the first thing I want to do is move my final potential energy over to the other side by subtracting it. So I'm going to have GHI plus 1/2 VI squared minus GHF equals 1/2 VF squared. All right, I want VF squared by itself, so what do I do now? Divide by 1/2. And then square root, because I'm looking for VF, not VF squared. Right? So what I'll have is 9.81 times 70 meters, my initial height, plus 1/2 times 38 squared minus 9.81 times 35 divided by 1/2. Okay, and then square root. Everybody good with that? All right. A little bit of a trick when you punch this into your calculator. If you're going to do it all under the square root, you've got to have brackets. Okay, otherwise it's going to mess something up. What I generally do is I just do one piece at a time. So I go 9.81 times 70. And then I go plus 0.5 times 38 squared. And then I subtract 9.81 times 35, which I could have shortcutted. I could have just gone 9.81 times 35 and not have the subtraction part in there. But hey. And then I'm going to divide that by 1/2, and then I'm going to square root it. All right, so when they hit the ground on the other side, they're going to be moving at 46 meters per second. It's 166 kilometers an hour. I would not want to try and control a dirt bike at that speed after having jumped across a canyon and fallen 35 meters. Okay, that would prove very difficult to control. Okay, as you will see in the video I'm about to show you. So the one I want to talk about actually has to do with the question you asked, David, about the vertical velocity, right, that he was falling. So what we've got in this video that we're going to watch is like a bomb being dropped, okay, from an airplane. So if I've got an airplane flying along, and it's flying along at, let's say, 150 meters per second, okay, when it drops the bomb, obviously it's got its initial height, and then the bomb will follow a projectile arc down to the ground. Okay? If I'm doing this as a conservation of energy question, where let's say we know what this initial height was, and let's say it's 10,000 meters. Okay? And I want to calculate the speed here when it hits the ground. I also need its initial velocity, or initial speed. Agreed? Okay, what's the speed of the bomb when it's dropped? Yeah. What do you suppose the most common mistake is on a question like this? That they say 0. because they think back to projectile motion, okay, where the vertical component of the bomb being dropped is 0 meters per second, and the horizontal component is 150. Projectile motion is a vector analysis of this movement. Conservation of energy is a scalar analysis of this. Your kinetic energy only has to do with how fast you are going, not what components are doing what, just how fast. That bomb's initial velocity is 150 meters per second, or initial speed, sorry, is 150 meters per second. Okay? And yes, as it falls, it's going to accelerate vertically, but its speed will kind of be the resultant between those two numbers. And it is going to increase because gravity will be making it go faster and faster. Okay? That sort of makes sense? All right. How many people have seen the movie Dr. Strangelove? Okay. It's very old. It's even older than me. And it's a lot older than me, actually. Okay. It's in black and white. That's how old it is. So it's actually a satire of the whole Cold War thing that used to go on between the Soviets and the Americans. And the context of this scene is that the war has kind of started. World War III has kind of started, and there's this lone bomber that's flying low to the ground under the radar through Russia, getting ready to drop its nuclear payload. And they've reached a peace solution, and they're trying to recall all of their bombers, but they can't get a hold of this one, and they're afraid if it drops the bomb, it's going to start the whole thing over again, kind of thing. So the crew is flying, they're paying attention to everything, and when they try to drop the bomb release fails. And they're very dedicated to their duty. So the bombardier decides he's going to make sure that bomb gets dropped. And he goes into the bomb rack and physically releases the bomb while sitting on it. Now, you may have seen this as a meme somewhere, a guy riding a bomb like it's a bull, okay? Like with the cowboy hat and everything.
Target distance 7 miles. Correct track indicator -7.
Roger, 7 miles. Track GPI.
Okay, so does that kind of make sense? And I only bring that one up because it happens a lot, and I've actually asked a question like that on the unit exam before, where I have a question about something like a person skydiving or something like that, and people get it wrong because they think that initial speed is 0. Its initial vertical velocity may be 0, but according to Newton's first law, you drop something out of a moving aircraft, it's moving the same speed as the aircraft at time 0, so it does have kinetic energy. Okay, everyone okay with that idea? All right, so we've done that example. And no, that's kind of too easy for us. All right, I would like you guys to try question number 1 here. Try 1 and 2, okay, for right now. And then we'll look at number 3, which combines projectile motion with conservation of energy. Okay, so they've got down in the question. Do they need that? Completely unnecessary. They're just indicating that this is just something falling, okay, instead of moving horizontally as well as falling, but it isn't important to the question because everything is scalar. We don't need vectors, okay? So we've got a mass of 55 kilograms, also something we won't need because we're not calculating energy. We would need it if they asked calculate the final kinetic energy because mass is part of that. But in this case, we don't need it. So we know its initial height is 225 meters. Okay, we know it's that it's moving at 36 meters per second. And we're looking for its, well, not velocity, but speed when it is 115 meters above the ground. Okay, so it's very much like the ones we've done thus far. We haven't done one where we actually had to calculate the height yet. Okay, is it a whole lot different? You just solve for h instead of v. Okay, but in this case here, we're going to have m times g times h initial plus 1/2 mv initial squared equals mg h final plus 1/2 mv final squared. Okay, mass can cancel, and we're looking for VF, so we're going to bring the GHF over here. So GHI plus 1/2 VI squared minus GHF equals 1/2 VF squared, and then we just plug in our numbers. All right, so we'll have, oh sorry, we got to do this yet. Divide by 1/2 and square root. All right, so when we plug in our numbers here, we're going to have 9.81 times 225 plus 1/2 times 36 squared. So there's our initial potential, there's our initial kinetic, minus 9.81 times 115, our final potential, divided by 1/2. Right, when we do that, we should end up with 58.8 meters per second. Right, and I mean, we can put down on there because it is falling straight down, but we don't need to.
It says velocity.
It does say velocity, which is weird, and I guess because it doesn't change direction, they can ask for that, but the speed and the velocity are equal in magnitude in this case. And you really shouldn't ask for velocity in an energy question because it's scalar. It should be speed. Okay. All right. Number 3 is going to combine some projectile motion stuff from Unit 1 and some conservation of energy stuff from what we're doing right now. So we've got the human cannonball being fired from the cannon. The cannon's 15 meters above ground level. They're going to fly through the air and land in the net. The net is 2 meters above ground level. Okay? They tell us that they're shot at a speed of 21 meters per second at an angle of 20 degrees above the horizontal from a platform that's 15 meters above the ground. So they're saying Acrobat has a mass of 56 kilograms. Okay? What is his gravitational potential energy relative to the ground when he is at the highest point in his flight? That is the part that requires you to remember something about projectile motion. Okay? Remember that they are flying through the air. And when they're at their maximum height, there's a couple of things we have to remember in order to calculate this correctly. Okay? And then for part B, if the net is 2 meters above the ground, how fast is he traveling when he hits it? No projectile motion stuff required for that one. That's strictly using what was given in the question, law of conservation of energy. Okay? So I'll give you guys a few minutes. Part A is the tougher part of the question. Part B is just what we were doing before. Okay, so there's actually kind of a couple of ways to go about it. Okay, if I want to calculate the potential energy at that point in the flight, I basically need to either know how high he is or how fast he's going. Either one of those will help me calculate his potential energy at that point. Okay, so I could go about doing this as a projectile motion problem, calculate the vertical components of his projected velocity here of 21 and 20. Okay, so I could set it up like this and say, all right, so this is 21 meters per second, right? Yeah, so this is 21 meters per second, 21 degrees above the horizontal, okay, and go, all right, this is V horizontal, this is VI vertical, and I could calculate the maximum height. And then I would just add that to the 15 meters.
I think the angle is 20.
Oh, sorry, it's supposed to be 20. Okay, so I can calculate VI, which I'll do right now, and I'll just go sine of 20 times 21. All right, so there's my initial velocity, 7.18 meters per second. What's VF at the maximum height? 0. Okay, so what I'm going to do is use VF squared minus VI squared, okay, over 2a, so I've manipulated it already, right? And if I do that, I'll have 0 minus 7.18 squared divided by 2 times negative 9.81. Okay, so 7.18 squared divided by 19.62. All right, so he's going to end up another 2.63 meters above the 15 meters he was initially shot from. Okay, so if I just go plus 15 meters, okay, now I have the height. Can I calculate his potential energy? Times 9.81 times, what was his mass, 56? Okay. what they got. Right? 9,683 joules, or 84 joules. Okay, that's one way to do it. Right? The other way to do it is to use the horizontal part. Because when he's at his maximum height, he's still moving horizontally. I could use that to calculate his kinetic energy and then just subtract it from the total mechanical and have his potential that way. So there's more than one way to do this. Okay? I could also just calculate B horizontal. So cos of 20 times 21. Okay, gives me 19.7. So, okay, when he's here, moving at 19.7 meters per second. So now I can say, all right, the mechanical energy, okay, is EK plus EP, and I'd have to calculate it somewhere else, probably initially, right? So I would go 1/2 times 56 times 21. That would give me the initial kinetic when he's launched, plus 56 times 9.81 times 15. So 0.5 times 56 times, 21 squared plus 56 times 9.81 times 15. All right, so that's the total mechanical energy anywhere in flight, that number. Anywhere throughout the course of this flight, that's how much mechanical energy he has, because EI equals EF, no matter where we are. Okay, so 20,588. So now that I have that number, I can now subtract his kinetic energy from that number, and I'll get his potential energy. Should still be this number. All right, so I'm going to go minus 0.5 times 56 times that number there, squared. Okay, it's pretty close. 9,684 in both cases. Okay, there's a little bit of difference because we use trigonometry, okay, versus using just strictly conservation of energy, but it's close enough that they're essentially the same answer. All right, everybody okay with that?
So which one is right?
Both. Either way, I've calculated their potential energy at the maximum height, right? Since both methods are valid, it's just a difference in kind of rounding, basically. Okay. All right, how many people have done part B? All right, I'm going to give you a couple more minutes on part B. You don't have to do any projectile motion stuff to do part B. It's just like the motorcycle jumping over the canyon question. All right, so part B works just like all the other ones we've done, okay? It's just an EI equals EF situation, okay, where we have, I'm just going to kind of shortcut here, GHI plus 1/2 VI squared equals GHF plus 1/2 VF squared, right? And we're looking for how fast they're traveling when they hit the net, so we're just bringing, so we got GHI plus 1/2 VI squared minus GHF, okay, equals 1/2 VF squared, okay, divide by 1/2, square root, we've got our manipulation done, plug in our numbers, and we got 26.4 meters per second. Okay, pretty straightforward stuff. All right, so tomorrow we'll probably kind of finish up conservation of energy, maybe even do power tomorrow, okay, because it doesn't seem like you guys are struggling too much with this. We'll do a few more. Got a quiz tomorrow. It'll have work energy and conservation of energy on it. Remember, your friction labs are due tomorrow. So make sure you've got them done, submitted by 8:30. You can submit them anytime once they're done if you want to, okay? But they have to be in by 8:30. And then probably do unit exam review Friday, because I feel like we're just scorching right through this. Okay, we'll do our lab on Monday and probably start unit 3 on Tuesday. I think that was our plan before, but that's kind of where we're at. Okay?